I'd like to thank Doug, and here he is, for instance, for helping me understand the EHP sequence better, and for showing me how to see the genus of a degree 4 plane curve without using Riemann-Hurwitz, and for being perceptive in all sorts of wonderful ways. The work that I'd like to tell you about is joint with Jesse Cass. And we're going to talk about defining Euler number in the Grothendieck bit group and using it to count lines on a smooth cubic surface. And I'd like to start by talking about the Euler number and also the Eisenbud-Levine-Kimshashvili signature formula, and then we'll do new things. So Euler number, if we have a vector bundle on a manifold, so let's let this be a rank R vector bundle, and X a smooth real dimension R compact manifold. We can ask that V be oriented, but let's weaken that a little bit and say that V is relatively oriented. And relatively with respect to this manifold. So what we'd like is an orientation of Hom from the top wedge power of the tangent bundle to the top wedge power of the vector bundle. And then let's take a section that only has isolated zeros. So S section of V to X with only isolated zeros. And the Euler number can be computed with this section, and it's a sum over the points in X which are zeros for the section of a local index or degree of the section, and this local index can be described as follows. We can choose, so here we're going to describe this local index, and we can choose coordinates on the manifold near P, and we can choose a trivialization of V, and we'd like these to be compatible with the orientation in the following way. So if we have coordinates near P that are, so near P on X, so P is a point on X, V is a bundle, so we can choose a local trivialization, we want these to be compatible with the orientation. So if we have coordinates, we have nice coordinates for the tangent space. So if we wedge our coordinates together, that gives us a nice element of that wedge RTX. And similarly for the wedge R of V, once we've chosen such things, we get this element of Hom, and we'd like it to be positive, and that'll make sense because when you have an oriented line bundle, we have these transition functions which are positive. We can tell when something is a square. We can tell when something is positive. And this means that now S is a function. It was a section, but now it could be viewed as a function for some open subset of Rn containing P to Rn. And so then we have a local degree. We have this, the degree function from homotopy classes of maps from Sn to Sn to Z. And we could take the degree of a map. We'll take a small ball so that there are no other zeros of our section that we assumed had only isolated zeros in this epsilon ball. And there are two things you could do. You could take the boundary, apply S, and look at its form and get a map from Sn to Sn. In anticipation of wanting to do things motivically, let's make a function from a pushout from this ball over this ball minus the point to R. I guess our rank was R. To R affine space over R of dimension R, and using the embedding of this in Rn, this is actually a map from a sphere to a sphere, so we can take the degree of this function induced by S, and this is our local our local degree. So there's a calculus way to say what that local degree is. So we can also take the Jacobian at P, which is this determinant of the partials of S. Since S is a function from R to R to the R to R to the R, we have these coordinate functions. So S is S1, SR, and we can look at the Jacobian determinant, and then it's a nice standard differential topology that if the Jacobian determinant is positive, then we get this degree is +1. If it's negative, it's -1. And then in general, the answer to what happens when the Jacobian is 0 was actually a contribution to math from 1978, which is long after the other. So in general, this is going to be the signature of a symmetric bilinear form that we're about to review this. And this is no matter what, so including, so J of P can be equal to 0 here, and it works otherwise. And this is the Eisenbud Levine Kimshashvili signature formula. Signature formula. This is Harold Levine, and we're going to talk about Mark Levine in a little bit. So the signature of a symmetric bilinear form over R is you can diagonalize such a thing, and you look at the number of +1s minus the number of -1s on the diagonal. So let's say what this is. Eisenbud in I guess 79 suggested defining this over an arbitrary field, so K, any field. And in the signature formula, we'll take K equal to R and get a symmetric bilinear form over R. And here's the definition of this symmetric bilinear form. It's on the following vector space. We're going to take the functions near our point. And so you can do these with the analytic function germs and do a power series. We're going to move towards algebraic geometry, so we're going to view these as polynomial functions. But if you'd rather do it in the context of smooth manifolds, please take your function germs. So this is the local ring of functions at the point P, all your function germs. So if you like, do this, and what we're going to take away the power series in a second. And then we're looking at this isolated zero, so we're going to divide by the coordinate functions of our section. S is equal to 0, so this is what the S equals 0 space looks like around P. And P is an isolated 0, just beating that there exists an open set U such that S is not equal to 0 on U minus P. And that's the same with some commutative algebra as saying that Q is finite dimensional over K. So we have a finite dimensional vector space over K given by our functions near S equals 0. Moreover, Q is a complete intersection. And that implies that it's self-dual. So the dual in Q modules can be identified with just Hamming Q to K is itself. And that's true for any Gorenstein ring. But for complete intersections, there's distinguished isomorphism. So there's a distinguished isomorphism. And the version of this that we'll use is Steger-Storch. And so we can let 1, which is an element of this ring, correspond to eta, and then this form that we set out to define, the omega EKL, is a symmetric bilinear form on Q. So it takes two things in Q and it spits out something in K. And if we took functions f and g in Q, these map under omega to eta of f times g. This is defined in families. So it's nice to have such a canonical way to write down omega EKL. But if we're just looking at the signature, all we need to know is the isomorphism class. And if we just need the isomorphism class, this is very easy to write down. So explicitly, and it's just as explicit when the characteristic is P, but it uses a distinguished Sokal element instead, and we have the Jacobian. So explicitly, what is this form in the Eisenbud-Levine-Kimshashvili signature formula? We take any eta, choose any linear map eta from Q to K, such that eta of the Jacobian is equal to the dimension of Q. And then you use the same procedure. So in particular, if your Jacobian was non-vanishing. So let's suppose that P is a rational point. So P has coordinates in K, and we suppose that the Jacobian at P is non-vanishing, which means that in Q mod the maximal ideal, it's not in the maximal ideal. Well, then this is smooth, and so you've got a smooth finite ring over K. So that means Q is just isomorphic to K. And so our omega EKL is going to take two scalars in K. And it's going to spit out FG times, well, the Jacobian is something in K star, and the Jacobian has to go to the dimension, which is 1. So this has to go to 1 over the Jacobian. And let's give notation for these symmetric bilinear forms. So notation. J will denote the isomorphism class, the symmetric bilinear form J K cross K to K, which takes FG to FG over J. So that is everything I wanted to say about the Eisenbud-Levine-Kibshashvili signature formula. At the end of this article, where Eisenbud was describing this work and suggested defining the analogous omega EKL over any field, he asked what would happen if we defined the degree in this manner. So define degree. So this is a question of Eisenbud from the same article. Define degree to be equal to EKL. And then he asked, is there an interpretation of this like a degree is in using cohomology? And there is. It's the degree in A1 homotopy theory. Yes. So there's an equality between this form and the local degree in A1 homotopy theory. And this equality takes place in the growth indeed fit group. So I'd like to define the terms on the right-hand side. So here's the definition of the growth indeed fit group. So GWK, we're going to take isomorphism classes of symmetric non-degenerate symmetric non-degenerate bilinear forms. And this has a tensor product and a direct sum, and we'll group complete with respect to direct sum, giving a direct minus, and then we'll get a ring. and which is the definition of this, and it has a presentation. So its generators are the bracket J in the notation on the right. So it has generators J for J and K star, and relation. There's just one relation in characteristic, not two, which says that J plus minus J is the same as 1 plus minus 1 for all J. This is quite explicit in a lot of cases. If, so if we changed basis here, so here we have K, and we have this scalar F, but if we changed basis to multiply by A, then this would become, say, F over A. This would become G over A, so this would be changed by A squared. So we can really take our generators J to be in K star mod K star squared, and then there's one relation. If everything has a square root, then your only generator is 1. Anytime you're algebraically closed, for instance, so the Grothendieck Witt group of C is Z via just taking the dimension, and the Grothendieck Witt group of R is Z cross Z, taking the rank and the signature, and the Grothendieck Witt group of FP is the rank, and then you can take the determinant of an associated matrix. And those are the two invariants which determine the isomorphism class. So we have more information than just in Z, and in many cases you can explicitly calculate this information. And if for an arbitrary field K, we have Milnor's conjecture, which gives us a lot of invariance on quadratic forms going farther and farther down some filtration, and they can be made more or less explicit, so you can get invariance that can be counted or calculated out of the Grothendieck Witt group. Well, so you could figure out the ring structure certainly here,
Before the
this is as a ring too, because then okay. So thanks. So Kyle's pointing out that for the ring structure, we get that as the ring structure. Thank you. And these should all be ring homomorphisms too. So what is the A1 degree? We have a homotopy theory where we can take homotopy classes of maps between schemes. And I wasn't planning to say too much about that, but if you take RPN or CPN, and it has a top cell, which is a sphere, and so we get some spheres in A1 homotopy theory, like so, and there are other spheres too. And Morel has a degree function from homotopy classes of maps from this sphere to itself to the growth in deep bit group, which is an isomorphism when n is greater than or equal to 2. And you can similarly define the local degree of a function. So if S from AN, or from AN to AN, the local degree of, so S has an isolated 0 at P, then we take U, a neighborhood U containing P, and we can make a function induced by S from U over U minus P to AN over AN minus the origin. And again, using tangent spaces, this can be identified using purity and the trivialization of the tangent space. We can identify these as maps from the sphere to itself. So we can then apply Morel's degree function, and then we have a local degree in A1 homotopy theory. So let's use this local degree and make an Euler number in the growth and deep bit group. So we'll give ourselves a relatively oriented vector bundle. So let's X be smooth, proper, compact, dimension R over K a field. Let's let V to X be a relatively oriented vector bundle, i.e. we have a line bundle, exists LX line bundle, and an isomorphism between the square of L and Hom from the top wedge of the tangent bundle to the top wedge of V. And let's let S X to V be a section with only isolated zeros. So we'd like to make the same definition. We'd like to say that the Euler number of V, and let's say with respect to S, we want this to be the sum over the closed points P, such that S of P is equal to 0 of some local degree. And the local degree can be defined as follows. We again want to, the same way as in the beginning, we'd like to choose a local trivialization of our vector bundle and local coordinates. That we don't have isomorphisms of local rings on coordinates to affine space with schemes. So let's choose a local trivialization of V. Let's choose an étal map, or étal coordinates, étal map from U containing P in X to AR. And we want this to be an isomorphism on residue fields. So we want the extension of residue fields, KP, and then we can call this phi to k. No, let's go the other way. We get an extension of residue fields, and we want this to be an isomorphism. So these are could be called Nisnevich coordinates, and they exist in a lot of cases. For instance, if you had a perfect field, if you had a separable extension of residue fields and R was greater than 1, and or if you had a covering by affine space of your X, which we will in the application. Here we've chosen some Nisnevich coordinates, and we want these to be compatible with the relative orientation in the same way as before. We take the top wedge power of the associated trivialization of the associated basis for the tangent space from the coordinates, and we get an associated basis for the top wedge power of V from the local trivialization, and we want it to be a square. And we know what a square means because we have this orientation. So these are compatible with the relative orientation. Unfortunately, not every function on U, like S is the section, S is a function on U, but not every function on U is pulled back from a function on AR. That's a nice manifold property that you get this isomorphism of local rings. And for étale coordinates, it doesn't necessarily follow that S is really now a function from AR to AR. But it is up to a high power of the maximal ideal. So by modifying S by R tuples of functions in a high power of the maximal ideal, let's call that P, S becomes a function on some open set of AR to AR. And this modification isn't going to change the local degree. So once we've got a function from AR to AR, then we can use our formulas for the local degree. So then defining our local degree. And to show that it's invariant of the choice, there's some finite determinacy results on the eta or the Eisenbud-Levine-Kivishashvili signature formula. We now have the local contributions, the local degree for this section, and then we can show that if we chose a different section that were connected by sections also with only isolated zeros in a family over A1, then this element of the Grothendieck-Witt group called the Euler number is the same. So we'd like this to be well defined for the vector bundle, not for the vector bundle in the choice of section. So the Euler number computed with different sections are equal if S and S prime belong to a family parameterized by A1 of sections with isolated zeros. if you can connect all your sections in that way, then you're going to get one Euler number for the vector bundle. There's an alternate approach that was developed this year by Mark Levine, not from the signature formula. And it uses oriented Chow-Witt or Chow-Witt groups of Barge-Morel, and also worked on by Fezel. And you can take the Chow-Witt groups of X twisted by a line bundle, and there are Euler classes. So given Vx vector bundle, there's an Euler class. In fact, there are a couple. You get a construction using the 6 operations on oriented Chow, and you have an obstruction theory Euler Euler class in. So if this is rank n on X, then we'll get an element of oriented Chow n X twisted by the determinant of the vector bundle. And these were defined by Barge-Morel and Morel, and they were further worked on by Fezel. And then they're equal up to a constant in the Grothendieck-Witt group. Maybe that's 1, as shown by Ashok-Fezel when the determinant is trivial. And then Mark Levine this year got rid of the trivial determinant condition. And then there's a push forward in oriented Chow. So let's let X be dimension R and proper. Then we can push forward well, let's do X to spec K from, if we take the highest wedge power of the tangent bundle to X, sorry. This is true too. But there's an isomorphism. There's a Bloch has a formula for Chow in terms of cohomology of Milnor K-theory, and we have an analog. We have the Nisnevich cohomology of X with coefficients in Milnor-Witt K-theory. And let's push forward in and we push forward by R, and we'll get H minus R X K Milnor-Witt N minus R. Oops, the push forward is spec K. So if we had a vector bundle such that when we took its highest wedge power, determinant V, that produced the same thing as this twist from the push forward, then we could get a class. So N equals R, we obtain a class or classes in the Grothendieck-Witt group of K. This is more powerful because you don't have the restriction on sections. The approach I outlined first has the computation of the local indices built into it. So I hope it's nice to have the two the two approaches, and presumably these are the same, and that should be written down. So let's use this to get more information out of counts from classical and numerative geometry that are picking up things about the arithmetic of the field. So, application to enumerative geometry. There's the count of lines on smooth cubic surface. So let's let F be homogeneous polynomial in 4 variables of degree 3. And let's look inside P3. Let's look at the locus where F is equal to 0. It's a 19th century result. Of Salmon and Cayley. So in 1849, Salmon wrote an article where he gives a lot of credit to Cayley for the case that if your ground field is C, in the complex numbers there are always 27 lines on S. And then in the 21st century, Koenig and Telemann and Venetian Varlamov observed that there's a lovely invariant count for real lines, but it's not the number of real lines. The number of real lines, so for k equals r, the number of real lines is not fixed. There can be 3, 7, 15, or 27 real lines. And one can see from tables where people compute all of these things so there are lots of great things computed about lines on a cubic surface. And there's a classical distinction between hyperbolic lines and elliptic lines. And you can see from tables from the mid-20th century that the number of hyperbolic lines minus the number of elliptic lines, this is for k equals r, is in fact invariant. No matter what the surface is, it's always 3. But Koenig, Telemann, Venetian, Varlamov seem to be the first people to observe that, and they gave the following explanation for this. So and these are all lines over R. So these are the number of hyperbolic real lines, number of elliptic real lines. their proof goes like this, and it's also based off of one of the proofs that there are 27 lines over C. So we'd like to count the lines on a smooth cubic surface. So let's look at all of the lines in P3. So let GW13 be equal to the Grassmannian parameterizing lines in P3, and this is equivalent to parameterizing dimension 2 subvector spaces of our fixed k to the 4, which we could projectivize to get P3. And on this, we can form the following vector bundle. So let's let V to the Grassmannian 1, 3 be the vector bundle whose fiber V over some subspace W. So let's say our dimension 2 subvector space will be denoted W in K4. And we'll take all of the degree 3 linear functions, degree 3 polynomial functions on W. So we'll take sim 3 of W dual. And our equation, cutting out S, so S was determined by this polynomial F being 0. So F determines a section of this bundle. So F determines the section S of V, where S on the dimension 2 vector subspace W is the function F restricted to W. So F is homogeneous of degree 3. It restricts to W. That's an element of sim 3 of W dual. And when does S, our surface, F equals 0, have a line? So the line L corresponding to W is in S, our surface. This was capital S equals 0. If and only if this section, little s, little s is 0 on W or L. So the zeros of our section correspond to the lines on the cubic surface. So the Euler number of V, assuming it can be relatively oriented, which it's not orientable, but it's relatively orientable. This is a sum over the lines L in capital S of the local degree at L of little s. And over C, everything is orientable. So this degree L of S is always 1. The corresponding local this local degree is always 1 over C, and over R, the local degree is 1 when you're hyperbolic. And minus 1 when L is elliptic. So we'd like to now count the lines on a smooth surface over an arbitrary field using the Euler number in the growth indeed bit group. So this is actually entirely classical. In here we're over R or over C, so we're actually just computing the local index of the vector field, like in the. Yeah. So to generalize this, let's give another definition of what hyperbolic and elliptic mean. We could use that as the definition of hyperbolic and elliptic, but there was a classical definition. So I see I'm going pretty slow here. So well, okay. So here's a classical way to distinguish hyperbolic and elliptic lines. So let's let L and S be a line on our surface. There is an involution classically associated to L, which switches P and Q if they have the following relationship to each other. So if we have P and L, we can form the tangent plane to S at P, and we can intersect this with S itself, and it has to contain L because L is a straight line, and then it has to contain something else of degree 2 because S is of degree 3, so there's some degree 2 conic C, and C intersects L in 2 points, P and Q, and I exchanges P and Q. So we have an involution on this line L, which is P1. So so I is then an element of PSL2 because it's an automorphism of P1. And elements of PSL2R can be separated into hyperbolic or elliptic, depending on whether they have their 2 fixed points are real or their complex conjugate. And this is, so hyperbolic, L is hyperbolic if and only if the fixed points of the involution are defined over R, but we'll say defined over K. And it's elliptic if they're defined over a degree 2 extension. So let's state the main result. Let's define the type of a line L. So now we'll let, so K arbitrary. Let's let the type of the line L, and now L is a closed point of the Grassmannian, because that was our definition of the Euler characteristic. And a closed point of the Grassmannian, it might be a line defined over an extension. But in any event, we have this involution also defined over that extension. And so we're going to take -1 in the notation from before, the A1 degree of the involution I. And there's also a trace map. So there's a trace map from the growth indeed bit group of the field of definition of our line, which might not be the ground field, to our ground field. The fields of definitions of the lines are actually always separable, and it takes a bilinear form. If we had some bilinear form B from V cross V to K of L, this trace takes this B to the form that goes V cross V and then does B, and then takes the field trace down to K. So we have a map from the growth indeed bit group of this extension. This lies to to the ground field. So the result let K be a field, it doesn't have to be perfect, of characteristic not equal to 2, then if you take the sum over all the lines, L in, let S be a smooth cubic surface, if you take the sum over all the lines of this trace from the field of definition of the type, as in that definition on the left, then you always get a single invariant element of the growth and Diegbit group, which is 15 times 1 plus 12 times negative 1. And if you apply the rank, you get the result over C. Implies the K equals C result from before. You apply the signature, you get the K equals R, the result that you get 3 hyperbolic minus elliptic. If you work with K is a finite field and apply the discriminant, then you get the number of hyperbolic lines with with field of definition FP 2A plus the number of elliptic. Again, there's only one non-square in FP mod FP star. So you're either hyperbolic or you're elliptic in the sense over here. Either your fixed points are defined over K or they're defined over the unique degree 2 extension of FP, which is FP squared. So that we get a definition of hyperbolic lines and elliptic lines. So number of elliptic lines with field of definition FP2A plus 1 is congruent to 0 mod 2, which is new. All right, thank you very much.